Okay, today we're going to begin exploring exponential functions. We have spent the first half of the year working on linear functions, which were straight lines. Now we're going to be looking at what it means to be an exponential function. So the way that we write our equations for our exponential functions is going to be y equals a parentheses b, and we're going to raise it to the x power. So when you see something raised to the x power, that'll let you know that it's an exponential function. So let's look at the difference in two tables. One is linear, like we've been working on, and the other is exponential. So when we're looking at this linear table, going from 2 to 4 in the y column, we're adding 2. The reason we know this table is linear is because we're adding the same amount to it every time. It has the same addition every single time. It's a constant rate of change. That's what we mean by linear. Now on exponential, if we look at this table, if I said plus 4, it wouldn't work for my next one. So what's happening really is we're multiplying. To get from 4 to 8, we're times 2. And again, times 2. So from 8 times 2 was 16. And 16 times 2, let's make this a little bigger, is 32. That's an exponential function. What's happening on it is you're multiplying by a constant ratio. You're multiplying by the same number every time. That makes it an exponential. So let's just practice making sure that we can identify exponential functions on tables. So this first one, going from 8 to 4. We can try linear. That would be subtracting 4, but it's not going to work the next time. So let's try exponential. Going from 8 to 4, we're multiplying by 1/2. So times 1/2. Or you could also say dividing by 2, but I'd like to keep it as multiplying because that meets our formula. Okay, so 4 times 1/2 equals 2, and 2 times 1/2 equals 1. So we have an exponential function. Okay, on this next one, we're going from 3 to 7. There's nothing I can really multiply going from 3 to 7, so let's check our adding. From 3 to 7 is plus 4. From 7 to 11 is plus 4. From 11 to 15 is plus 4. So that one is linear. Let's go ahead and write this. This one's exponential. This one's linear. Okay, pause the video, and I want you to figure out number 3 and number 4, and then start the video and check your answers. Okay, so we have one more linear and one more exponential. Now let's look at equations to determine if they are an exponential function. And one thing that I didn't point out to you that actually becomes very important as we get into this part is when we wrote the form of the equation. We have a parentheses b to the x power. But what's really, really important here is that b has to be greater than 0, but not equal to 1. And a cannot be 0 or we don't have anything. So this is the big key here. B has to be greater than 0. So when we look at number 5, it kind of depends on what is the a and what is the b. If the a were -1 and our b was 6 to the exponent, that is an exponential function. So we'll put yes. However, if this were a was a 1 and the b was a -6 raised to the exponential function, that's a no. So really we're not sure on this one because it depends on which way it was intended. where was the negative sign? Did it go with the A or did it go with the B? But it's really critical to get in your head that if you've got a negative B, it's not an exponential function. Okay, so let's go to this next one. We've got another one of the rules is the B cannot equal 1. If you go back up here to our rules, B cannot equal 1. So when we look at this right now, very clearly they're saying B equals 1, so this is a no. Okay, our next one over here, we've got 7x to the third power. That's not exponential because it's always 7x to the third power. So nope. We would need this power to be to the x. Okay, so now we're going to evaluate the function. In other words, we're trying to find a specific answer. So it says evaluate the function for the given value of x. So we have a function. Our function is y equals 3 raised to the x power. So it's an exponential function. So what we're going to do is we're going to put that into the y equals key of our calculator. So put it into the y equals key. And then we're going to do second table. And we're going to go to our table where x equals 5 and see the answer. So that's the way we always evaluate exponential functions. So I'm going to go ahead, pause the video. I'm going to evaluate numbers 8, 9, and 10 and write down the answers. You evaluate them with your calculator, start the video, make sure you've got the right answers. Okay, the big thing to notice when you're evaluating these is how fast the numbers either decrease or increase. Okay, turn the page. So now we're going to start looking at graphing our exponential functions. And the real interesting thing is, if you look at these pictures, this first one is going so that our b value is greater than 1. So it's actually growing. So if you look at this, our b value in our ab squared has to be greater than 1. On this one, our b value is between 0 and 1. Now remember, on an exponential function, it can't be less than 0. So this is between 0 and 1. Okay, so let's actually look at graphing a couple of these. So on this very first one, we want to graph, I'm going to make it bigger, we want to graph the exponential function 2 times 1/4 raised to the x power. So what I'm going to do is I'm going to enter that into my calculator and I'm going to look at some of the points. And from looking at my points, I see that I want to actually draw my axis right here and right there. So there's my XY axis. And when I'm looking at my points, I've got -1, 8, 1, 2, 3, 4, 5, 6, 7, 8. So I'm going to put a point up there. I've got 0, 2. So 0, 1, 2. That's my y-intercept. I've got 1 and 0.5. So it's going to go about right here. I think I need to change to red. I've got 2, 0.125. So 2 is getting a little bit closer. And 3, I've got 0.03125. So they're getting closer and closer to 0. But what's interesting about this, an exponential function, is when I graph it, it's going to get closer and closer and closer to 0, but it's never going to touch 0. 0 is like our boundary. Asymptote is the same thing as a boundary. So when I graph this, and if I look at my table, the numbers get smaller and smaller and smaller, but they never touch 0. So my asymptote is y equals 0. It's a horizontal line boundary that this graph will never cross. Okay, and we already looked and saw that our y-intercept is 0, 2. Now let's talk about domain. Notice on domain that we've got on both sides, domain is read left to right. On the left side, we have an arrow. Even though it looks like it's going straight up, it is ever so slightly going further and further to the left. So our domain on an exponential function is always going to be infinity. But range changes a little bit because we have an asymptote. So we know this is never going to touch 0. So our range is the y has to be greater than 0. We know it's going to go, top is somewhere forever, so infinity, but we know that our bottom is never, ever, ever going to touch 0, so it's greater than 0. Okay, well, let's look at another one. All right, our function this time is negative 2x. Now, since we already know that our b cannot be negative, when I put this in the calculator, I'm going to put it in as negative 1 times 2 raised to the x power. That's the only way this is going to work out in my calculator. So when I put it in and look at my graph, it helps me make a decision on where in this picture I'm going to draw my axis. So I'm going to draw my axis with my x-axis here at the top, and I'm going to put my y-axis right here. And the only reason I've picked these two spots is it gives me the most of this graph to put my points on. So then when I look at my table, I have way out at negative 3. Negative 3 is 0.125. So that's way, way up here, but not touching 0. Negative 2 is 0.25, so a little bit better. Negative 1 is 0.5. Then I get to 0, my y-intercept, and I'm at negative 1. So I can see it's starting to curve down. At 1, I'm at negative 2. And at 2, I'm at negative 4. 1, 2, 3, 4. And at 3, I'm down at negative 8. 5, 6, 7, 8. So we can look at it. My graph is never, missed it, never touching the y-axis. Notice that. So my y-intercept right here at negative 1. So 0, negative 1. My asymptote, my boundary is at 0. We already know that domain on these things, I'll put my arrow, is infinity. And the range, when we look at this, we know it goes on forever at the bottom, but it's never going to reach 0. So it's going to have to be y is less than 0. Okay, so now let's look at a couple of real life applications, because this is more likely the kind of stuff that you will see when they start testing you on this. So they've given us a graph of a bacterial population. One of the great exponential growth experiments is on bacteria. And they want us to write the exponential function that represents the population. So this is a good time to start talking about what the A means, what the B means, because we're going to need to write an equation in A, B raised to the x power. So the A, actually I'm going to make this bigger. So the A is our y-intercept, and the B is our ratio, the number we're multiplying by each time. B is the ratio. So when we look, I'm going to go ahead and put my data into a table, because I can see things a lot easier if I've got a table. So I've got 0, 3, 1, 15, 2, 75, 3, 375. I'm not going to write the last one, I'm out of room. But when I'm looking at my table, to get from the first y to the second y is times 5. And then I got times 5 and times 5. So I know that my ratio is 5. And my y-intercept, that's where x is 0, is 3. So I can go ahead and write my equation as a, which is 3, parentheses b, which is 5, raised to the x power. So now it's asking me to identify the y-intercept, which we've done that, and to explain what it means. So to explain what it means, we really just need to see our x represents days, and our y is our bacterial population. So at 0 days, our bacterial population is 3. That's all our y-intercept is saying. Our domain and range, this is a little different because we're now in a real life situation. Our domain starts at the left. Now we know that if this were not a real life situation, this graph would go on forever, never touching the 0. But if we look at what x is representing, it's representing days. We can't have negative days. So we know that our very far left has got to be 0. So its domain is actually going to be 0 less than or equal to x, and then it's going to go on for infinity. I don't know that we really have infinity days, but we don't really have anything to stop it if they feel like growing this bacterial thing forever. So I'm going to go ahead and put infinity. So really our domain is x is greater than or equal to 0. And as far as our range goes, we know that it's never going to touch 0. So our range is greater than 0. So y is greater than, but never equaling, just greater than 0. And then it says find the population after 5 days. Well, the way to do that is to look at our function. We need to put it into our y equals key and look at the table. And when we look at the table and go to the 5th day, our population is 9,375. Okay, so that's just looking at it in a real life situation. Let's go ahead and do this coffee one because this is looking at real life in a whole different way. So here we have a table, and this table tells us the temperature of our coffee after so many minutes. But when I start looking at trying to come up with the common ratio, I can already look and see this is going to be messy numbers. So I'm going to show you real quick how to put it in your calculator. We can use stat edit. Let's move this up. We can use stat edit on any exponential function. Remember, the two things you have to have is it cannot be a negative b, and it cannot equal 1. The b cannot equal 1. So we don't have either one of those, so we can use stat edit, and then we go stat calculate. We've been using 4 for linear, 5 if we didn't know if it was linear or quadratic. Now we're going to use 0, which is for exponential functions. So I'm going to put this data into my calculator, into stat edit, and I'm going to go stat calculate 0. Let's go ahead and pause the video, get that done, and then we'll talk about what it all means. Okay, so when I put it in my calculator, I came up with A being 174.95. This would be a slight decimal rounding error, but if we look at this, our y-intercept, or our starting temperature at 0, is 175, which is what that rounds up to. And then I have a common ratio that is just as ugly as it can be, but that is the common ratio that works with this exponential function. Then I went ahead and went into my y equals and used my VARS key to copy this information in so I didn't have to remember all these decimals. And when I pulled up my table, now I've got information. So I've used the graphing calculator, which is what Ace said, to find the exponential function. And now I'm going to use that data, I've put it into my y equals key, to predict the future. And I need to predict the temperature of the coffee after 10 minutes. So I'm just going to go to my table now that I've put in the function. And at 10 minutes, it says my coffee is going to be 59.3 degrees in temperature. So 59.3. Okay, so that's the way that we can use exponential functions in real life. If you have any more questions, feel free to come into tutoring and we can talk about it more.